Hello, everybody. Thank you for joining us today. My name is Emily Kuda. I'm Percona's Senior Manager of Marketing Programs. We're going to get started in just a moment. For those of you who are joining us today, can you raise your hand using the hand icon to let me know that you can hear me okay? Great. All right. So next during this webinar, you are going to be on mute. Should you have any questions during the discussion, go ahead and enter those into the questions field down below. At the end of the webinar, we'll take time to answer as many questions as we can. After the webinar, we will send an email that will have a copy of the recording and the slides. So with all of that said, I'll turn the floor over to Peter Zaitsev. He'll be talking today about performance analysis and troubleshooting methodologies for databases. Peter Zaitsev is our CEO of Percona. Take it away, Peter.
Hey, thank you. Thank you, Emily. Hello, everyone. Let's get started. Well, and first, let me start by saying is what performance are very frequent, database are very frequent performance troublemakers, right? That is what they both cause performance problems, and then those problems can be quite painful to deal with. Now, why databases are painful in this regard? Well, one is what they generally have non-linear scalability. If you think about your, let's say, web application, often if you want to have 3 times more users, you just go ahead and then you have a 3 times more application servers, right? And they have 3 times more traffic. For databases, that is often not how it works. As you get more users, you get more data, queries scale in various non-linear ways, and so on and so forth. Databases are also generally quite complex systems, and they're also quite poorly understood by developers, right? What exactly is going on inside out there, and why this database is slow today, then that worked quite well yesterday. So when you speak about the performance work of databases, we can use about doing different things with it, right? Which require us to perform the analysis and troubleshooting. One is a plain troubleshooting, and what I mean by that is, well, if things just stop working. They work today, yesterday, they may be working half an hour ago, and now database got sick and things are not working properly, bad performance, we need to troubleshoot that. We also often need to perform a capacity planning, and that means we want to understand how much capacity database has, how much load it can happen, because in the end, any database, whatever well tuned and designed it is, if you put too much load on it, it will would have a very bad performance, right? If you overload it, and eventually you would not will become unavailable. Another thing which we have to do with databases is to look at the cost and efficiency optimization. That is especially important those days in the cloud, where your costs instantly kind of hit your pockets if you are not having your database or well optimized. And also in most cases, if you can optimize your database, you can immediately realize savings by reducing the number of database instances or using the smaller instance sizes. And the last one is a change management. And change management, I mean, both from a database standpoint as well as application standpoint. If you upgrade the database, right, or change hardware, operating system, you deploy the new application version, all of those are changes which often have significant impact of performance, which you may need to analyze and understand it well. The second thought I want to share with you is the points of view, which we'll talk through this presentation. One is your black box approach to the databases. And this is what I also qualify as your application developer. Hey, there is a, the database, it just something which serves my query. I don't really look at how it works inside. And then there is a white box, which is your DBA, or SRE or some other operations focus point. So from developer point of view, The database is pretty much as a black box, right? You, from your application, connect to the database, then you start sending queries to it, and then it just works. Now, what is interesting, though, in this case, the recent trends, especially with cloud deployments, with database as a service, you can have this black box point of view on the operational side as well. Let's say you're running Amazon RDS, it kind of says it's doing your database backups. You kind of don't know how, may not quite really care, as well as it does that, and you know you can restore from backup, you can be happy enough. If you look about the black box criteria for our successive databases, we think about what application developer would care about, right? And these are typically availability, right? I mean, if you can't connect to a database, right, and run the queries, that is a problem. Response time. If queries queries run too slow, then the developers would be unhappy. The correctness, that is also important one, because it's very easy to make any database very kind of lightning fast, right? You can just make sure you delete all the tables from it, and all your queries will be lightning fast. Will just throw you back the error, right? Incorrect response. But otherwise, it will be fast. So we cannot really look at response time alone without considering what we want the correct response. And finally, as we spoke about the cost as well, even if you don't really understand how a database works internally, you're running databases, right? And you are, or somebody on your team is likely to be getting invoices every month, right? To understand how much that all costs for you. From an operations points of view, you often would look also at various things which are internal or kind of white box, right, for the databases. You can look at the load for different resources, resource utilization such as CPU load, and so on and so forth. You would look at various system and hardware problems, right? Maybe there is hard drive malfunction and so on and so forth. And you also often would look at the specific methods for scaling and capacity planning. Okay, now as we go through with that, some of the high level the ideas, right, and terminology, let's look at some of the specific methodologies for performance troubleshooting and analysis. Now, if you look at the most companies, right, how do you think the databases are troubleshooted? Right. Well, in my experience, it is done by random Googling. Right. You have a problem, you get your best description you can come up with in the Google, and hope you get the answer out there. Now, while many simple problems can be resolved through Googling very easily and effectively, it is not a great approach, because that is a hard to assure outcome. Right? In some cases, that's you'll get an answer pretty quickly. In some, it's not. It's hard to train people in this case, because that's kind of not very structural. It's also hard to automate. If you want to make sure what large or at least some of your problems are in the environment are handled automatically. I would also state that in some cases, which approach can be dangerous. Because while a lot of advice you can find in the internet is good, there is also a lot of advice which is bad, which is unhelpful, and will be time waste for you, or even more, it is dangerous. Right? For example, you may be getting database performance, but you they will trade the safety for that, and if you ever get, let's say, some crashes, you may lose your data, right? Without knowing so. Okay, now if you want to do better, we can deploy one of the methodologies to save a day, and there are quite a few methodologies which exist of them for databases and otherwise. In this presentation, I will focus on 3 which have been making waves quite recently. One is use methodology, by Brandon Gregg, then there is red methodology by Tom Wilkin, and also golden signals method, which was championed by Robert Evachuk. So what is use method? Use method was specifically developed by Brandon Gregg to troubleshoot server performance issues. And it is designed to resolve 80% of problems with 5% of effort, right? So this method is not intended to be complete, showing everything, right, resolving every single problem possible, but for majority of problems, it can help them to resolve them very efficiently. Now, the Brandon Gregg himself would state what he would suggest it to apply the use method. And if that happened to be one of those about 20% of the problems you cannot resolve with this method, you can use some more complicated analysis method, for example, such as method R, which is, I would say, designed to be resolving larger set of problems, but it is much more evolved. What is also great about use method is that there are a lot of operating system specific checklists are available, right? That is one of the reasons it can take just 5% of the effort to do those things, to do that for problem resolution. Okay. So if you want to talk about the use method with a simply one sentence, it can be summarized like this. For every resource, we want to check utilization, saturation, and errors. Okay, let's look at more specifically for terminology which is being used here. What are the resources? Resources are all your physical server functional components like CPUs, disks, buses, network interfaces, and so on and so forth. What is utilization? Utilization is the average time was resource was busy servicing work. And in this case, we mean the average percent of the time resource was busy servicing work. The saturation, a degree to which the resource has extra work which it cannot service, right? Often queued, right? In majority of cases, when you cannot really immediately service a work, then we would have some queuing which introduces an extra response time, extra delay. And the error is obviously count of the error events. What do we see here as a resources? Resources would be our CPUs, socket cores, hardware threads. In terms of memory, that's the memory capacity, your network interfaces, storage devices. For storage devices, we can look at kind of like two distinct resources. One is capacity of device to do I/O, right? And if you cannot if you're trying to do too many reads or writes from device, right, more than it can handle, then the system will run slow, right? At the same time, if you will try to use more disk space when it's available, then you'll have even an error, right? Or system can go down depending on how it's set up. Controllers and interconnects is another resource type which exists. Okay, now how does this use method can be used with software? With software, the same basic resources would apply, right? If you have a software program and it's use a lot of CPU, right, then that can perfectly be bottleneck or using too much disk I/O and so on and so forth. But there are also additional software resources which apply. For example, mutex logs, right, can be seen as their software resources. And if you have a lot of contention on the mutex log, you can see that mutex log being kind of busy or utilized, right? And then from that you can see what that is a hotspot. File descriptors, that is another important logical resource, right? Because if you run out of file descriptors, then the programs would likely malfunction, right? Or a crash. Network connection is a similar example. Okay, we spoke about the use method benefits, which is a proven track record. It's broadly applicable to a lot of systems, and also there are a lot of details checklist available. What kind of drawbacks does come with a use method? Well, one is it really requires a good understanding of a system architecture, right? And if you look at more details use method description, it'll say, well, why don't you start with your functional kind of system diagram, which outlines whatever resources exist in this case and what are dependencies with them, right? If you don't know that, then it's maybe hard to apply the use method. Now, it also may require access to the low-level resource monitoring. For example, you may want to be able to get the information about CPU usage, right, or network usage, or low-level errors with your network or hard drive, right, for that error counter. So, which may be hard, especially hard in more of your service. I would say like a black box environment, as often exists in the cloud those days. Now, when you apply use method to cloud computing, I think there are another things you have to consider, because in this case, in addition to looking at the resource utilization limits, you often have to look at your limits in place, which are placed to isolate the tenants from each other. So, for example, you may have certain C groups limits set up on the Linux side, or some hypervisor limits, where you may not be granted to access of all CPU resource available, or all memory, and so on and so forth, right? That's need to be used as a the resource, your true resource limit, not the all resources available. And then you also need to highlight what the true hardware information, right, about resource utilization may be only available on hypervisor level only. You may not, depend on the setup, you may not have a very exact understanding of the physical resource usage. Now, the next thing I want to highlight is the queuing, or that kind of saturation point. Now, if you guys wonder what the hell is this picture and what does it have to do with queuing, right? This is a fractal. And why I put this picture here, because I think the understanding on this queuing often is almost like looking at a fractal. The more you zoom in, the more level of details you start to absorb, right? In this case. And then when we speak about the basic method, right? In this case, we speak about their utilization and saturation, and it implies a very simple approach, right? When it comes to resources. Either your resource is service and request, or the request, right, is being queued, right? Now, the reality though is, as you zoom into the system, you may find is what you consider kind of being serviced at one level, maybe actually being in the queue waiting on another level. So, for example, you may be thinking is what you have a certain program, right, function running on CPU, but it's actually waiting on the memory bus because it has a cache miss, right? Or you may see the process as being running, but actually it's in a CPU, in operating system CPU queue due to operation. You also, from your logical standpoint, you may say, hey, you know what, this is my disk IO request, which is in the process, right? It's kind of sent to the underlying subsystem. In reality, though, it can be waiting on a network if that is a network connected storage, right? And there are a lot of those kind of different levels which exist out there. What I want to kind of take away from that is what you really, when you're thinking about whatever of a queuing happening, or there is something is in flight and being processed, you need to kind of to pick the level of of abstraction, right? And whatever makes sense for you, and stick with that. Okay. The next thing I would point out is using use method for Linux. A lot of those same approaches are very helpful for the databases as well, because a lot of the database performance problems would often be connected to their high use of some of your base resources, which you can basically jump from a Linux level. Here is some of the examples Brandon provides, as well as a link to more detailed checklist for a Linux operating system. Now, let me also show you some of the graphs what we are using from our tool at Percona called Percona Monitoring Management. And Percona Monitoring Management is our 100% free and open source monitoring solution, which is something you can use both in the cloud and on a premises environment, and is really purpose-built for open source database monitoring. Though you can use that to monitor the bare Linux file system as well. It's designed by us to be really focused on the easy to set up, and it's also built on leading open source monitoring technologies such as Grafana and Prometheus. So when you speak about the utilization for CPU, there is a very simple graph you can use, right? I mean, I think pretty much any monitoring application out there would be happy to show you CPU usage graph, right? With pretty much breakdown by different CPU usage modes. Now, what is I think more interesting though, is to take a look at the CPU saturation, right? Because the 100% CPU usage may correspond to basically almost nobody's waiting, or you may have literally 100 of different threads, right? Different processes which are waiting on CPU to get access to that. And we provide that information with a normalized CPU load graph, which is your pretty much CPU saturation measure, how many there are running programs per core are available. And generally, in a good sense, you want to have that on, 1 or below, right? That tells there is no queuing. In this case, it's kind of slightly above 1.5. That means there is a little queuing happening, but not too high. Another thing what is very often becomes a problem for programs is how much is when one of the CPU cores becomes overloaded. And in this case, we can see one of the CPU cores has been pegged, right? So the CPU was quite busy. And in many environments, you'll find while your overall CPUs, looking at all cores, they're not busy, but one or a couple of cores are completely saturated, right, and causing performance bottleneck in some cases. Another nice view, which kind of summarizes the two components which Linux use to compute load average, is runnable process and block processes. So, for example, in this case, we can see this system has always, more than 10 process running, right, with a few process waiting on disk I/O, but at some point in time, there was some event where a lot of process have been waiting on disk I/O, right, which can indicate the problem. Physical memory is an important resource. Now, in terms of Linux, especially, it is kind of a little bit tricky to monitor this resource utilization, because often you would have very few small amount of memory which is seen as free, right? But you will have a lot of memory which is used as cache and buffers, with significant portion of that is being reclaimable, right? But if you really get to a very short end of that, with no buffers or memory buffers or cached memory are available, then often that can be the problem. What I like to look as well is at the virtual memory utilization. The virtual memory tells us how much memory is available, both including physical real memory as well as swap. Now, why is that important? Well, of course, we don't want the systems to swap, especially something like a databases. But at the same time, swapping will have a performance impact, but that would not have a database crash. Now, if you run out of a virtual memory, typically what happens, then the database process would be killed by out-of-memory killer, right? And the database will become unavailable until the kind of a crash recovery completes, right? Which may be, several minutes or more. That is something I personally would like to avoid, unless there is some, great failover mechanics implemented, so that is non-event for application. Another way you want to look at their at the memory, right, or virtual memory resource is through swap activity. Really, in many cases, you want some of the swap file space to be used, because often in any operating system image, there would be certain pages, certain processes, right, which are not really used after system has booted. And it's good to be able to swap them out to have some free some memory available. What you don't want to have is a very specific, very high swapping activity going on, right, all the time. So, for example, in this case, you can see we have very little swapping activity, just less than kilobytes a second in average. So that is not a problem at all. In terms of a disk I/O, looking at disk I/O utilization, you can, of course, use the utilization graph, which is very similar to what VMstat provides. What I like looking in the case here is disk I/O load, which is pretty much similar to a load average, right? It tells us to see how many in-flight requests there have been on disk in average at that point in time. And what we do here, we break down that between read load and write load. Why do we do that? Well, because depending on what kind of storage you have, there may be different ways to optimize for reads and writes, right? And there may be cases where some malfunctions, for example, cause your writes to become much, much slower, right? While your reads are not impacted at all. Related graph, what you can use is disk I/O latency information. And we can see in this case what we are looking at both average latency, right, for period of time, which you can think can be a little bit volatile, right? That's all those dots. But we also provide the average latency for over last 1 hour, and that can show you what is sort of, let's say, typical latency which device shows. In many cases, when you run into some problems like an overload, right, or something, you would have right, or maybe some physical problems, right, like SSD device have to do some very intensive garbage collection, right, or something like that. Then often you would see a lot of you would see that kind of sustained I/O higher than average, right, or average would gradually spike. For for network traffic, network utilization, that is a pretty easy, right? We can see how much network traffic is being used both for inbound and outbound. In this case, what I think is much more interesting is how do you think about the network errors, right? Network problems. And I like to think about that from a two distinct standpoint. One is your local network errors, pretty much your network interface errors. How many packets you had to drop because of a queuing, right? How many packages you couldn't receive because of a queue overflow, maybe errors in transceive or transmit or received because some corrupted frames and so on and so forth. Now, if you have a well-architected network, local network, which you don't overload, you should see a graph which is something like this, where you pretty much have zero local network errors. Now, if you have your servers communicate to each other over a wider area network, even if it's just like a few switch in between, then you would likely to have some problems which correspond to the segments retransmits, right, as we can see here. And this is quite important to look and monitor because in many cases you would have some bad performance problems which are driven by network correlated to a spike of number of retransmitted segments and especially a ratio of retransmitted segments. So keep that in mind. Now, if you look at the MySQL side, how do we look at what kind of work MySQL is doing, right? What is exactly the inflow of work so we can think about its capacity? And from this standpoint, the very basic definition of work would be number of questions. Pretty much number of queries per second MySQL is getting. That is a good high-level understanding, right? And everybody understands, hey, you know what, my MySQL has 10 queries a second, right? Or 10,000 queries a second, right? But reality is the queries can be very different. You can have a query which just looks up a row by the primary key, right? Or a single row from a memory by a primary key, which is very simple and cheap, or you can have a query which traverses maybe many millions of rows, right? In this case, it's often a good idea to look at the lower level about work which is being done by the database, to look at the row level operations, like we look at the InnoDB row operations in this case. And while not all rows are being equal either, rows are typically much more similar to each other compared to the queries. Now, if you look at the MySQL from a saturation standpoint, right, it is good to take a look at number of threads running. Threads running in MySQL talks about queries which are being in flight, right, or being processed by MySQL at the same time. Right now, as I mentioned before, that is where your understanding what processing from MySQL side, may not be the same as actually being processed as running on CPU. Right, many of the queries may be processed by MySQL side, but they may be actually locked on locks. Locked waiting on disk I/O, right, or waiting on available CPU core, and so on and so forth. Still, I think that is a very good measure of a MySQL saturation, because if you have much more threads which are being running, then you have number of CPU cores, right? Then the chances are you have some weights going on. And there are some different tools you can use also to examine what exactly is happening to the MySQL queries. Okay, so we got a lot of illustration and a lot of insights for use method. And frankly, that is my favorite method and the method I'm the most familiar with. But now let's look at the other methods as well. What is about the red method and what is it designed for? This method is designed for systems which are based on the microservices and they are treated more as a cattle, not pets, right? Or your resources are treated as cattle, not pests. And if somebody is not familiar with this analogy, is what in a kind of classical or old world, depending on your point of view, we used to have, let's say, a server. We kind of, just buy one or couple of servers. We really install them very carefully. We kind of tested them and really care what each and single one of them is really very healthy every day, right? And this is like pets, right? The cattle analogy is, hey, you know what? I just have a big herd, right? Maybe thousands, right? Maybe more of different instances. And you know what? I don't. I care about the big numbers. I don't really care about where, wherever one of the members of a herd, right, is malfunction or not, right? The statement in this case is, hey, you know what? If it gets sick, shoot it in the head, right? Well, and that is exactly how we manage servers or containers in the cloud. If you have a instance on Amazon, for example, which is malfunctioning, right? You don't have to diagnose wherever that is your newly updated RAID firmware conflicts with your newly updated Linux kernel. You don't do this stuff like that. You can say, well, you know what, screw it. I'll just shut this instance down, get the new one, right? And off I go. What is also interesting in this microservice environment is of a mapping of resources, right, can be quite fluid. So we may not quite, as environment changes, we may not really even have that information about this fixed specific resource we have. So red method instead looks at a high level abstraction. We can say, well, let's look at our microservices and for our services. And for each of those services, and we can check for look at requests which come to those services. And for each request, we can check the rate of errors and the duration or response time distribution, right? So if you look at red method for databases, then there are some interesting implications here. One is if you look at any grand scheme of things, because the databases are well, kind of contain your data, we kind of have a really complicated failure modes where we want to ensure we don't lose any data. Then the databases often are not quite cattle, even in an environment where other components as web services are. And in this case, we can apply the red method both looking at the service level, right? And if, for example, have some load balancing across the multiple databases, as well as looking at the individual databases. For example, at least so we can figure out if one of the database nodes gets sick, and so we can dispose of it, right, and replace it. It also can be applied to some components and resources, right? For example, you can think about how many reads or writes a given table is taken. And that also can be applied to the individual type of queries, right? Well, I think it even should be applied because the response times or rate of different queries is important for us to understand the system performance, right? Because we're not have not the same performance properties. So what are the benefits we have for this red methods? Well, it's easy to map to what developers care about, right? If you think about what we have for the red method is very similar to what we spoke about at the start. Hey, you know what? We want our particular requests to be fast and come with no incorrect, right? With no errors. It doesn't also require a deep understanding of the infrastructure. You don't really need to understand how microservice works internally to understand if it's sick or not, right? And it also doesn't really need access to low-level resource monitoring. Now, the drawbacks I would say in this case, where it does not have much tools or checklists to support yet, and it's also more focused on answering what rather than why. So it can figure out, oh, you know what, this microservice is malfunctioning. Go to the people who wrote this microservice, right, and let them figure out why is it going on, right? Or possibly you can then apply the use method, right, to deal with resources or systems on which that particular microservice was deployed. I mean, those different methods, they don't conflict with each other, right? It's not like you have to pick one or another. Now, we spoke about what the red method can be well applied to their specific queries. And let me show what PMM can help us to do in this case. So for PMM, per corner monitoring management, we can actually see the response time, right, and the counts, right? You can see the count and the latency for all the different query times, the types what your system is getting. In this case, we are showing the top 10 queries based on load, but you can look more. And then for every query, you can actually get not just the average response time and how that response time average change over time, you can also get the information about response time distribution. Right, like in this case, you can see what this query was an average about 4 milliseconds, but 95 percentile for that was 18 milliseconds. Right, so you can really get some ideas about the distributions here. We also provide a global summary of query response time latency, which I found the most helpful to observe the slow queries, right? Like in this case, we plot the slow queries of different kinds, like your moderately slow queries from 10 milliseconds to 1 second, queries which are quite slow, 1 second to 10 seconds, and queries which are, oh my gosh, so slow, right? More than 10 seconds. And looking at those different query classes often can be very, helpful to understand how your system performs, right? And hopefully you don't have any of those very slow queries. Okay, now let's jump to the four golden signals methodology. This really comes from the SRE book, right? Site Reliability Engineering books published by O'Reilly at this point, I think, and specifically the monitoring distributed systems. And it's really designed kind of to be used for alerting, troubleshooting, and trend analysis. It really says what you should be focusing on 4 golden signals. And again, you will find there is a lot of overlap while using slightly different terminology with the use and read methods. Latency, right? For latency or response time or duration, right? Kind of the same stuff pretty much. We want to look at the distribution, not average. And what is important here is what you want to track latency for successful requests separately from errors, right? Because otherwise you'll often get, hey, you know what, or you'll often get the cases where system kind of becomes like behaving sort of like duopolic way, right? Like you get some percent of requests, let's say 10%, which are error, but they're quite fast, and there are other requests which are, return successfully, but they may be quite slow, right? It's good to understand that scenario separately from saying, hey, you know what, I mix errors and non-errors together, and that gives me kind of a reasonably good response time. Traffic, which is how much demand is being placed on the system, right? How much, right? And that's something what we track versus capacity, right? And errors. In terms of errors, we obviously look at the error counts, but often it's very helpful to look at the error codes as well. And in many cases, these are very important, right? Because if you are looking at the deadlock error, right, that is one thing. That's kind of common operational problem. If you have a lot of errors which say, hey, that is an incorrect query syntax, then that make a response to either bad application being deployed, which is not forming queries correctly, or maybe it corresponds to somebody is trying to break into your system using SQL injection, right? So understanding different codes is very important. Now, it's also important to understand what some errors, they will originate in a bad content, not the error code. And figuring out when query return wrong content is actually very hard in general. You can do some checks, some basic check in some cases, but that's not completely. And saturation is how full is your system capacity, right? Now, in this case, the best idea is to make sure you have performed some capacity planning in advance, because in this case you can really get some more ideas, right, about how far you're close to your capacity. If you look at the golden signals for databases, latency, we speak about query response time distribution by digest, as I show you. Traffic, you also can look at the number of queries of a specific kind served. Again, that's the same table I show you. Errors, that's your error codes, but from queries or from connection attempts, but also your wrong query responses, which are, well, frankly, quite hard to figure out. And in terms of saturation, that is a lot of your resource usage, where you can find, like being limited by CPU, by disk I/O, and so on and so forth. But also logical things like connection is very often important to measure, right? Because if you run out of database connections, well, you know what? You won't be able to connect to database and run your queries anymore. Now, if you look at the benefits of this golden signals methodology, this methodology works well. It's tested by Google and many others, right? The Google is example on which site reliability engineering book was written about, and there is a good book resource available, which is also fantastic. Now, in terms of your drawbacks, it's kind of a framework for monitoring mostly. It doesn't really go into the very in-depth understanding about why given thing is causing the problems, and there are no specific troubleshooting checklists for that exist as of yet, as they exist for use method. So if you look at the takeaways from me here, there are the great innovation happening in the performance analysis method, and it's very good to see what over last few years we have number of them has been originated. Some of them are specifically tailored for microservices, right, and in new ways how you deploy deploy things in the cloud. And you also probably can notice what there is a significant overlap between them. A lot of them are looking mainly at the same things, just in a slightly different way. Okay. With that, I wanted to make a couple of announcements before we move to questions. One is Percona Live conference in Frankfurt. We will have a conference in November 5th to 7th. The call for papers is opening soon, so if you have a story to share about open source databases, not necessarily MySQL, MongoDB, right, or MariaDB, we really at Percona love and deeply care all open source databases which exist out there. With that, I also want to announce or remind to those who already see the announcement is what Percona supports PostgreSQL starting July 1st. So we are very happy to add another fantastic open source database technology to our family of support technologies. And with that, Emily, I would be happy to take some questions.
Great. Thank you so much for that, Peter. All right. So our first question is, what is the right method to use if we want to track long-running processes on a database? Should we scrape the MySQL process list per process or per state? And what is the right metric here to track?
Well, if you want to look at a long running MySQL processes, typically you would query like performance schema show process list, right, to see schema and catch the processes which are more than certain amount of seconds which you consider long, right? Some people care about queries which take more than 5 seconds, some more than 60, right? And in this case, typically you store them and you analyze them. In many cases, what you'll find valuable is to understand the source of them. Maybe that's host, maybe that's user, maybe that's information about the tables they touch, right? So you can, diagnose and resolve, right? Why are you having those extra slow statement? Now, I would point out that that is a good idea to do that in addition to analyzing your slow query log, because if a query is just slow, it will be in a slow query log, right? If a query is something which you'll never complete, right? Like if it's way too bad, you may not see it in a slow query log until it's too late, right? I've seen many performance problems when people would have, I don't know, let's say 5, 10, 100 runaway queries running on the server, right, and completely bogging it down. So good idea tracking that.
Thank you. Let's see. Our next question is, do you know if Bracona will be supporting Cassandra databases anytime soon?
Well, I would say thank you for your request. In this case, this is not at a roadmap, but we are evaluating what would be the next database technologies for us to support. And if you have some interest, I would encourage to talk to our sales team, because the customer demand is really what is driving our choice and also the timing of our technology support roadmap.
Thank you. Let's see. Our next question is how to troubleshoot the query execution time.
Well, how do you troubleshoot the query execution time? The best thing in this case is to, well, I would say the two things in this case. Now, if you're using the PMM, right, you should be able to see what the query execution was, right, and various diagnostics data, how many rows it scanned, how long it spent in disk I/O, and so on and so forth. That can give you some ideas. Now, what the other approach to look at that is to run explain. Right, you would run explain for a query, and then you can understand to what extent this query is being run optimally, right? Is it using the appropriate indexes and so on and so forth? Generally, the bad running queries can be of two kind of different classes. One is a query which is just purely optimized. Maybe you forgot to add the indexes somewhere and so on and so forth, right? And that's something you would catch with explain, right, and fix it. There are some other queries which are just expensive. So for example, you may have a query which runs, let's say, group by on 10 million rows, right? I mean, whatever you do with that query itself, it will still need to scan and summarize so many rows, right? And that takes a lot of time and effort. In those cases, you can either allocate more resources, right, to make those queries faster. For example, scanning 10 million of rows is bad, but it's much faster if the data is in memory compared to if you have to do a lot of disk I/O, right? Or you can use some other techniques, right? So for for example, in the same case, maybe you can cache that value, right? Or build a summary table instead of running that expensive query over and over again.
Makes sense. Thank you. Our next question is, how could we deadlock a history? Would you need to retain it for a couple of weeks, or is it possible that MySQL seems to retain only the last week?
Well, I'm not quite sure what do you mean by MySQL retaining deadlock history. Now, if you look at the MySQL, there are two things which are available, right? Or not actually like three things. There is a deadlock counts available. So you can see how many counts you have, and typically spikes in the deadlock counts, they are indicative of some problems. In many cases where so application changes or bad query performance can really spike the number of deadlocks. The other thing you can use is show InnoDB status in MySQL would show the latest deadlock discovered. And here you can use a tool from Percona Toolkit, which can log the deadlocks, right? It can just like sample the InnoDB, showing the status to store all the fresh discovered deadlocks. The third method is what you also can look at the MySQL slow query log, and it would log the deadlocks with a specific error codes. So you can from that see what kind of queries are causing the deadlock, and you can store the slow query log time, right, and what's not for as long as you want.
Great, thank you. Our next question is, in Galera cluster, if we want to achieve consistency in our operations where reads made from a different node other than write nodes, how do I measure the latency in sync from master to other master nodes?
Oh, well, yeah, that is a question which is not quite quite connected, I think, to our today presentation. But generally, the Galera, right, it has the measurements of a latency, like the average and max latency for query, for internal query replication, right, which is available from show global status, right, or PMM also have a graphs in the PXE section for that. Now, I would also point out, if you're just concerned about the making sure you don't have a stale reads in your application, I would ensure what you use causal reads, and not relying on what the data will be propagated in the PXE cluster within a certain amount of time, right? That's timing is just very unpredictable.
Great, thank you. Let's see. Our next question is, how to improve the performance for heavy load queries in MySQL?
For heavy what?
Heavy load queries.
How to improve performance of heavy load load queries? Well, let me give that is a very general question, but let me give you some highlights. Right, generally you want to make sure you optimize your queries, making sure they use the proper instances and a query in schema are more well designed, right? That is typically your best time for back. Then do not use MySQL for things it's not designed well for. So, for example, if you want to run the query which needs to aggregate 10 billion rows, use something else. Use Hadoop, Spark, use ClickHouse, right? Or if you're in the cloud, BigQuery or Redshift, right? MySQL is not going to handle those very well, right? And then there's also proper MySQL tuning settings, and finally the hardware, right? I mean, their powerful hardware with MySQL decent amount of memory, fast disk, can really make the 10x performance difference compared to the something which is mid-range one.
Thank you. Okay. I'm going to record the last few questions because we are actually at the top of the hour. But thank you so much, everybody, for attending today, and we hope to see you on future webinars. And thank you so much, Peter, for attending today and presenting.
Okay, thank you, Emily.
Thank you. Bye.